After studying this chapter, you will be able to explain charged particles, understand atomic energy levels, define energy bands in crystals, discuss metal, insulator and semiconductor. Hello students, let us have a look at our 10th chapter, that is electronic devices. We will first try to understand what are electronic devices. Our kitchen today has many electronic appliances like the electric kettle, toaster, sandwich maker, roti maker, the electric cooker, mixer, grinder, blender, electric chimney, microwave oven, refrigerator. Oh, the list does not seem to exhaust. All these devices have shaped our life. Our living standards have improved. Now, did you know that these devices have electric charges? These devices have electric charges which are positive or negative. An electron is one of the fundamental particles constituting the atom. The charge of an electron is denoted by -e. The magnitude of E is 1.6 times 10 to the power -19 coulomb. The mass of an electron changes with its velocity in accordance with the theory of relativity. An electron which moves with a velocity v has the mass m as given, where c is the velocity of light in free space and c equal to 3 into 10 to the power 8 meter per second. If v is less than c, then m is similar to m0, which is called the rest mass of the electron. The rest mass of the electron has the value m0 is equal to 9.11 into 10 the power of -31 kg. The radius of an electron is about 10 the power of -15 m, and that of an atom is 10 to 10 m. The radii are so small that electrons and atoms are ordinarily taken as point masses. Charged particles. Physicists notice something very particular, that the light given out by a hot solid such as tungsten filament has a continuous spectrum. The light given out by a hot gas such as sodium street lamp or neon sign has a discrete spectrum. It is like the difference between the notes when you play a violin versus a piano. So why does this happen? We start by making this bold assumption that energy levels in an atom are quantized. An electron bound in an atom can take only certain exact energy levels. It is forbidden to occupy any other energy level. The electron can be excited to go to higher energy levels. Whenever the electron falls from a higher energy level to a lower energy level, a photon is emitted. The energy of the photon is equal to the difference between the two transitioning levels. So the quantization of energy levels in an atom means that only photons of certain energies can be emitted. Now, since the wavelength of a photon is related to its energy by E equal to hc over lambda, the quantization of energy levels in an atom means that only photons of certain wavelengths can be emitted by the gas atom. Energy bands. Let us take a look at the classification of materials based on energy band theory. To understand the behavior of solids, we need to know about the three energy bands, namely valence band, conduction band, and forbidden band or forbidden energy gap. Displayed here is the energy band diagram of a conductor, insulator, and a semiconductor. A conductor is a substance which has a large number of free electrons. When potential difference is applied across a conductor, the free electrons move from negative terminal to positive terminal of the supply, constituting electric current. Conductors allow electric current to pass through them. For example, copper, aluminium, brass, nichrome, and all metals are conductors. In fact, in metals like copper and aluminium, the valence band and the conduction band overlap in such a way that there is no forbidden gap. Potential difference across the conductor results in the movement of free electrons. Insulator is a substance that does not allow the flow of electric current through it. In terms of energy bands, the valence band is full while the conduction band is empty. The energy gap between the valence band and the conduction band is very large. As a result of this, high electric field is needed to push valence electrons into the conduction band. The electrical conductivity of such materials is extremely small. It can be regarded as almost negligible. Diamond, wood, glass, paper, etc. are insulators. Semiconductor is a substance whose electrical conductivity lies between that of conductors and insulators. According to the energy band theory, the valence band is almost filled and the conduction band is almost empty. But the energy gap between the valence band and the conduction band is very small. Therefore, a small potential is enough to push the electron from the valence band to the conduction band. Now at low temperature, semiconductor behaves as an insulator because of empty conduction band and full valence band. Semiconductors. Semiconductors are the elements of the periodic table that exhibit high conductivity at high temperature and nearly zero conductivity at low temperatures. Silicon and germanium are the two important semiconductors. Now let us try to understand how current flows through the semiconductor. This is how a germanium crystal is represented. The distribution of electrons in a germanium atom is given here. At absolute zero, all electrons of the semiconductor are tightly held. The inner electrons are bound, whereas the outer electrons are engaged in covalent bonding. At this temperature, covalent bonding is very strong. Hence, there are no free electrons. Therefore, the semiconductor crystal behaves as a perfect insulator at absolute zero. At room temperature, due to thermal agitation, some of the covalent bonds are broken and the electrons are available for conduction. The absence of electrons is represented by a small circle called hole. We observe that the movement of electron and hole are opposite in direction. Now this is how a silicon crystal is represented. The distribution of electrons in a silicon atom is given here. At absolute zero, all electrons of the semiconductor are tightly held. The inner electrons are bound, whereas the outer electrons are engaged in covalent bonding. At this temperature, covalent bonding is very strong. Hence, there are no free electrons. Therefore, the semiconductor crystal behaves as a perfect insulator at absolute zero. At room temperature, due to thermal agitation, some of the covalent bonds are broken and electrons are available for conduction. The absence of electrons is represented by a small circle called hole. P-N junction and diodes. Let us now talk about P-N junction and diodes. To increase the practical utility of a P or N-type semiconductor, a P-N junction is created in a semiconductor crystal. Here, one half is P-type and the other half is N-type. P-N junction is the arrangement obtained when a P-type semiconductor is joined to a N-type semiconductor. Now this is a P-N junction. Immediately after it is formed, the P region contains holes which are mobile and negatively charged ions which are immobile. Now the N region contains impurity ions which are immobile and mobile electrons. Many electronic devices use P-N junction. As soon as a P-N junction is formed, electrons from an N-type material and holes from P-type material diffuse in to P-type and N-type material respectively. The electrons and holes diffuse into each other and combine near the junctions. Each recombination eliminates an electron and a hole. As a result, the positive donor ions in the N region and the negative acceptor ions in the P region are left uncompensated, and this region forms the depletion region. The region of a p-n junction containing the uncompensated acceptor and donor ions is known as the depletion region. Now this region is so named because it is depleted of mobile charge carriers. The holes trying to enter the P region are repelled by the uncompensated positive charge on the donor ions, and the electrons trying to enter the N region are repelled by the uncompensated negative charge on the acceptor ions. As a result, potential difference is established across the junction. Now soon it becomes large enough to prevent any further movement of charge carriers. This is called potential barrier or junction barrier or height of the barrier. From the figure you can see the potential barrier VO that is set up gives rise to an electric field that prevents the respective majority carriers from crossing the barrier region. Let us now see what happens when the negative terminal of a battery is connected to P-type region and positive terminal to N-type region. Do you see any deflection in the ammeter? You see, as no current flows through the circuit, the ammeter reading is 0. This is because the negative electrons in the N-type region get attracted to the positive terminal of the battery, and the positive holes in the P-type region get attracted to the negative positive terminal of the battery. That is, the reverse bias removes the majority carrier, which increases the potential barrier. Current flows through the junction if the p-n junction is connected to the battery as shown here. Holes and free electrons enter the depletion region due to repulsion at the respective terminals. The reduction of the potential difference causes a large number of majority charge carriers to diffuse across the junction. Holes travel to the right and electrons to the left, constituting a current in the same direction. Thus, the p-n junction allows current carriers to flow through it if the junction is forward biased. A device that allows the current to flow only in one direction is called a diode. So you see that a p-n junction can be described as a diode. Diode as a rectifier. You can see on the screen a sine wave as the input, but at the output half the wave has disappeared. We get only one half of the wave. Can you guess what could be inside the box? Yes, you got it. Right, it is a diode. Let us talk how the junction diode behaves as a rectifier, why it allows only the positive half cycle to go through and why it stops the negative half cycle. The circuit symbol for a diode is a triangle pointing from P side to N side. A diode is a p-n junction. Coming back to the disappearing half waves, see for the positive half cycle. The diode is conducting. So as the diode is conducting, we get an output for the first positive half cycle. Now during the negative half cycle, the diode is reversed biased. In that case, the diode will not conduct. So as there is no current flowing, we get a zero output. Again, during the next positive half cycle, the diode is conducting, so we have an output. During the negative half cycle, once again, the diode is reverse biased and we have zero output. So the output is only in one direction. There is no output for the negative half cycle. The output is now said to be rectified as it shows only one direction. Logic gates. Let us now talk about logic gates. A gate is a digital circuit which either allows a digital signal to pass through it or stop it. It is known as a logic gate because it allows the signal to pass through it only if certain logical conditions are satisfied. Okay, now we shall move on to the truth table and Boolean expressions, a table that shows all possible combinations of inputs and their corresponding outputs combination for a logic gate is called a truth table or a table of combinations of that logic gate. George Boole devised a different kind of algebra called Boolean algebra that deals with logical statements having only two values, namely a true or false value. In Boolean algebra, 1 denotes true statement and 0 denotes false statement. The three operations employed in Boolean algebra are OR operation, AND operation, NOT operation. These are the representations of OR, AND or NOT operations. OR gate. This is one of the basic logic gate which works on the OR operation of the Boolean algebra. This gate has more than one input and only one output. The Boolean expression is y equals to A or B. Shown here is the circuit diagram of OR gate. The circuit consists of two junction diodes D1 and D2 such that the N region of both the diodes are connected at one common point. Displayed here is the truth table. When A equals 0 and B equals 0, then Y equals 0. Now as the output is 0, the bulb does not glow. AND gate. This gate works on the AND operation of the Boolean algebra. It has more than one input and only one output. The Boolean expression is y equals to A and B. Its circuit diagram consists of two junction diodes D1 and D2 such that the P region of both the diodes is connected at one common point. Displayed here is the truth table. When A equals 0 and B equals 0, then Y equals 0. Now as the output is 0, the bulb does not glow. NOT gate. This gate works on the NOT of the Boolean algebra. It has only one input and only one output. Its Boolean expression is y equal to A bar. Its circuit diagram consists of a common emitter transistor. Displayed here is the truth table. When A equals 0, then Y equals 1. Now as the output is 1, the bulb glows. Transistor as a switch. When we talk of a switch, what comes to our mind is a toggle that is used to turn a circuit on or off. Now you know that in the on position, current flows through the circuit, and in the off position, no current flows in the circuit. Now this transistor here can also act as a switch. It seems strange, but it can. The switch on the right has to be mechanically placed in its on and off position by use of our hands. But in case of a transistor, an electrical signal is used. Now if we have an input pulse, then it turns the circuit on. Current flows in the circuit. If an LED is placed in the circuit, then the LED is going to light up. Now if there is no pulse, then the LED goes out. This means that there is no current in the circuit. So you see that the transistor here is acting as a switch. It has an on and an off condition. In the on condition, maximum or saturation current flows in the circuit, whereas in the off condition, no current flows in the circuit. We do not have an intermediate state, either the transistor is fully on or fully off. Let us talk in detail about it now. A transistor can be made to operate in three modes: the active mode, cutoff mode, and the saturation mode. In the active mode, the transistor is used as an amplifier. So when a transistor works as an amplifier, the values of the voltages and resistances are adjusted so that it works in the active region. Whereas if we have to use a transistor as a switch, the values of the voltages and resistances are adjusted in such a way that it operates only in the cutoff and the saturation region. Let us now look at the circuit to see how the on and off states are achieved. Over here what we have is a NPN transistor. This is the emitter, the base and the collector. The input is controlled by the input pulse, which we will apply. First, let us take a look at the off state. In this state, the input pulse is 0. When the input is 0, then the base is at 0 volts. You see that the emitter is already at 0 volts. This means that the potential difference between the emitter and the base is 0. Now, if both are at 0 volts, then the base emitter junction is not forward biased, so the base current will be 0. This will be true as long as the base emitter voltage is less than 0.7 volts. Think of this base emitter junction as a diode where the collector is 0. This base emitter junction is reversed biased. Now the output voltage VCE equals to VCC minus ICRC. Now since IC is 0, then VCE equals to VCC. So if there is no current in the circuit, that is IC is 0, the LED will not light up. Now this is the off state. Let us consider the on state. In this case, we have an input pulse. So current starts flowing provided the voltage of the pulse is greater than 0.7 volts. Now as the base current increases, the collector current also increases. This you can see from the graph. Now the output voltage is equal to VCC minus ICRC. So as ICRC keeps increasing, VCE keeps decreasing. Now the values of VCC and ICRC are chosen in such a way that VCE is equal to 0. So in that case, IC is equal to VCC over RC. Now this is the saturation current that is flowing when the transistor is in the on state. In this on state, since a current IC is flowing in the circuit, this LED is going to light up.